Welcome to the Massey Dialogues. Bienvenue. My name is Nathalie Des Rosiers and I am the principal of Massey College. Massey College is a place of ideas, and its mission is to nourish learning and serve the public good. Massey College, the place, is built on indigenous land, the land of the Huron-Wendat, the Seneca, and the Mississaugas, and we're always very grateful for the opportunity to continue to work on this cherished land, particularly in these difficult times. So Massey Dialogues is not only a response to the sense of dread that is occupying our minds these days with COVID-19. It is a response to many conversations that I've had since I became the principal of Massey College last August. To serve the public good, we need to have bridges. We need to establish bridges between cultures, between disciplines, and between generations. So that's the point of Massey Dialogues, where you're going to discover great research, great ideas, great researchers, but also we will practice intergenerational dialogues and interdisciplinary dialogues, and at times intercultural dialogues. So that's our objective, is to help ourselves understand and serve the public good by building these bridges and becoming better at it. So now I have to ask you to be indulgent a little bit, because this is our second installment of the Massey Dialogues. We're still working through the technological challenges that this poses, but we are very grateful. And I am very, very grateful to my guests today and to the audience. So today we will work in the following fashion. I will introduce our main guest, Dr. Barbara Sherwood Lollar. She and I will talk a little bit about her research, her discoveries, and then I'll invite a junior fellow, so the voice of youth, to come and say how this research matters to him and what does it say to him. And he is not from the scientist background particularly, so it's even more interesting to see how does it speak to him in his particular interest. And then finally, we will have Dr. Guo, who is a chemist, who will then intervene as well and make her comments about what's the impact of this research for her work and for society in general. So after that, we will ask for your questions. We will continue to talk, the four of us, but you're welcome to send us questions. You can write your questions in YouTube on the right-hand side, and then I will kind of ask them to our guest as they pop up on the screen. So don't hesitate. We want this to be a conversation with the audience as well. So let me just begin by introducing our guest, Dr. Sherwood, Dr. Barbara Sherwood Lollar. She is the 2019 Erzberg Gold Medal winner. She's a professor of earth sciences at U of T, a fellow of the Royal Society of Canada and of London, a very accomplished scientist who has many honors. She's a companion of the Order of Canada. She leads the science group at Massey. That's another big honor. and she also is on the governing board of Massey. She's a very busy woman who has also a research group. I've heard her explain her discovery before, and it's so fascinating. I couldn't resist the opportunity having Dr. Sherwood Lollar on the first week of Massey Dialogues to explain to us her area of research and her discovery. So let me start by my first questions. Exactly, can you tell us about your journey through this search for the earth, for water in the earth, and what did you eventually discover?
Yeah, thanks, Nathalie, and thank you all for this opportunity to reconnect with our community in the midst of all of this. We're all still here. We're all still engaged with each other. The tools that we're using to keep that engagement going have obviously changed, but I think it's clear both at Massey and U of T and Canada in general, we're all still here, connected and reaching out. So I very much appreciate this opportunity. You used the word journey, and that put me in mind of some terrific advice my dad had given me when I was a youngster, thinking about and frankly worrying about decision making. Every step of the way, thinking, am I going to make the right decision? Where do I want to go? What will my path be? And one of the very useful things he did that really helped de-stress those decisions is to point out that, in fact, each of these is a journey. And at each point, you just figure out the next step. The way he put it actually was stick your toe in the water. See what you think. If you don't like the temperature, take another path. And I think that that is not only an extremely good analogy for how to go about decision making. Don't sweat it so much. Make the best decision you can and move forward, because you can always come back. But it also really describes and answers the question you asked, because in fact, there was no point at which I thought this is what I would be doing today. And in fact, there are still moments when I look at what I do and have to pinch myself, because it's hard to figure out how you got from being a young kid who was interested in all kinds of things. I think basically had a sense I was interested in science, but really I think if you'd asked me, I would have told you I wanted to be an explorer, because I had parents who were both, my mother was an English teacher and then a history professor, and my dad was a French history professor, and they inundated me with wonderful books, and amongst them the Jules Verne books. Mm-hmm. So I think if you'd asked me at 8 or 9 or 10 what I wanted to be, I would have told you I wanted to be an explorer. And it seemed naive at one point, but when I look back and realize now, 35, 40 years later, looking back, 50 years later, looking back, I realized that that actually does very nicely explain the scientific journey I've been on. We have a sense that science is all about putting the next brick in the wall of knowledge, but sometimes you do actually, like at Harry Potter, open up a wall you didn't know was there and discover something fundamentally different on the other side. And the deep water that we found in the earth is of that nature. It really is older than any flowing water we had once thought could be.
So how did you go about to discover this? Can you give us a little bit more context about what was the technical way in which you got to discover this deep, old water?
Yeah, there are two aspects to that, I guess, both access and then technique. The access is an important one. When you work in the deep subsurface of the earth, unfortunately, we're not as fortunate as the oceanographers who can get a submarine and go down or send remote vehicles. In our cases, of course, how do you get, because I do work on the continents, so how do you get 2 and 3 kilometers deep within the continents? You can access these systems through boreholes, but those are few, far between, and expensive. And so typically, actually, what we have had the incredible fortune of working closely with the mining industry, because mines around the world, particularly in the very old continental rocks that we work in, like the rocks of the Canadian Shield, have many, many active mines, and some of them are amongst the deepest in the world. So we actually go down with the miners. That's how we get 2 and 3 kilometers deep. And then in terms of what we actually do, we're chemists at heart. I'm a geochemist, a chemist working in the earth, but nonetheless, our techniques are largely chemical. We're measuring the chemical constituents of these waters, and in particular, measuring something called the isotopic signatures. And by measuring all of that and putting together multiple lines of evidence, we're able to estimate the age of the fluids by what's there and also by what's not there. Because water that comes from surface has certain very specific characteristics associated with it. And so if we can find none of those surface indicators, that's our first clue that we're looking at something that's been isolated from the surface on long timescales.
Well, that's fascinating. So we have this old water down in the depth of the continents, and I know that your research has suggested that may be a possibility that other planets may have similar old water. Can you talk to us a little bit about that? How do you go from the Earth to the other planets?
Yeah, well, it's sort of fun for Canadians to understand that in many ways, our own Canadian Shield, the ancient rocks of our craton that occupy, of course, large components of the country, of the central part of the country, are in some ways a really good analog for Mars. Mars is, in some ways, what I refer to as Earth's evil twin. About 4 billion years ago, when life arose on Earth, Mars was probably a pretty good-looking place. And have you been looking in on our solar system and seen Mars in the way that we now realize Mars might have existed 4 billion years ago? It was probably much warmer, much wetter. It actually had an atmosphere. Because of a variety of reasons, Mars actually then lost all those things. It first lost its atmosphere and then became the cold, dry desert it is today. One of the other major differences is it never developed plate tectonics. So all of the rocks on Mars are old, just like our Canadian Shield. It doesn't have young rocks. So if you want to study Mars, you need to find rocks that are billions of years old. And as Canadians, we are blessed. We have some of the largest real estate that satisfies that criteria. If you go to the next step then, as I mentioned, Mars lost its atmosphere. If you lose the atmosphere, then any of the water on the surface rapidly is lost to space. We understand that life as we know it needs water. The only place where we're likely to still have liquid water on Mars is in the subsurface. That's the only treasure box in which that water could have been retained. So if we think about understanding Mars as a planet and the potential history of life on Mars, then you need to understand water in the subsurface. And so that's why our investigations in ancient rock, ancient water, stored in the subsurface of our planet on billions of years timescale, actually holds answers to some of the questions about life on Mars.
And does it also extend to other planets, or is it just Mars that is probably the evil twin that the analog is closer?
Well, we're living in a really marvelous time in terms of the information coming back from the rest of the solar system and beyond. What we know now, not only about the other planets in the solar system, but the moons, the multiple moons around those planets, particularly the moons in the Jovian system and the moons around Saturn, and then extending out to exoplanets. We're understanding that the diversity of planetary systems is much broader and wider than we knew. So not only are there rocky planets like Mars, but there are also all kinds of things we refer to as either the ocean worlds or icy planets, planets that have actually oceans and ice cover over the entire planet. There, too, there are analogies, because in those kinds of systems, once again, the subsurface is going to be a more protected environment to a certain extent. So we need to understand what it is about the presence of water, the interaction of the water with its environment, which in these places is rock, and what that might mean for life in these systems. So it's a question we call habitability. It's an investigation of the planetary environment to see if it could support life. And then the actual looking for life is a second question.
And I know that you're working with NASA as well. But on this note, I want to invite Michael OShea to join in, because he's interested in planets. And let me introduce a little bit Michael here. So he's a native of Chicago, but he now calls Toronto home. His PhD research at University of Toronto is on the relationship between treaty law, the Jay Treaty of 1794, and Indigenous education and Indigenous access to post-secondary education. So he was before an associate with an executive search firm. He's also served as education officer with the U.S. Embassy, working to ensure that both Canadians and Americans could engage in research and postgraduate education in the other country. He's been a researcher and an advocate for access to public parks for low-income neighborhood, and he's been a college counselor in Philadelphia in Canada. He worked as a big brother, and he holds a master's in higher education from the University of Pennsylvania, studied at McGill and at Pomona College. And he's currently a junior fellow at Massey College. Now, the reason why he volunteered and jumped on the occasion to be on this dialogue is that in his free time, he enjoys basketball, he plays the accordion, and he organizes for Massey public astronomy events. Hashtag PopScope. So I want to invite, so Michael, welcome, and it's so wonderful to have you to discuss this. So what does it speak to you? What do you get from the research of Dr. Sherwood Lollar?
And first off, I just want to thank you for that generous and interesting introduction, Principal Des Rosiers, Dr. Lollar. It's great to be here. It's an honor to meet you virtually. I was so excited to be invited to be part of this virtual event today. I find your work so fascinating. So as Principal Des Rosiers said, by day I'm working in the education space, but by night I like to organize public astronomy nights. So when you talked about this extraterrestrial water, my brain gears started turning. And I was wondering if you'd be willing to talk about what the sort of legal framework might be for any discoveries of water that could perhaps contain life on another world. So if you, say with partners at NASA, did discover water, and perhaps there was life or building blocks for life in this ancient water on Mars, I'd be curious to learn about what the law might say for that discovery and who it would belong to. Would it belong to Earth? Would it belong to you?
Yeah. I'm not a legal expert, but this much I can tell you. I am always careful about dating myself. Is Men in Black still something that people are familiar with? Series of movies. Okay, great. Men in Black is a giant in-joke. They are the Office of Planetary Protection, right? And they are planetary protection officers for the planet Earth. Those are real positions. That's a real place. In Washington, D.C., you in the United States have a planetary protection officer. She's a wonderful woman. Her name is Lisa Pratt, Dr. Lisa Pratt. She was dean at Indiana University. Before her was Cassie Canby. There is a treaty, an international treaty of planetary protection that is signed by Canada, the US, the European states, almost all of the people involved in space research around the world many years ago came together and developed a treaty of planetary protection that governs both the exploration side, what our planet might do to another planet. So it sets the boundaries about what you can take to another planet. And then it also covers the back end, which is the idea of what you need to do to protect our planet from something coming in. So although the details of the legal aspects of it, unfortunately, Michael, I'm not expert enough to be able to probably give you chapter and verse on the specific aspects. But I can tell you that that framework exists in the context of the Planetary Protection Treaty. And they do tend to wear the sunglasses because it's such a great joke. They're not Will Smith, but they do. Each of them gets an honorary set of sunglasses and a black suit when they get the job.
Terrific. Thanks for that response. I think there may have been a recent sequel to Men in Black too. So hopefully the next generation is also aware of this.
Oh, that's right.
Important
That's
position.
right. Yes, I haven't seen it, but you're right. It continues.
Yeah. Oh, thanks so much for that response, Dr. Lollar.
So, Michael, if you're in your group, did you know that? Did you know that there was old water on Mars, possibly, and therefore that could suggest that it may have been habitable and so on? And were you intrigued as a kid about Martians?
Yeah. Well, I didn't make the connection between ancient water on Earth and ancient water beyond Earth. And sometimes when you're busy looking up at other planets or other objects in the sky, you forget how marvelous and interesting the Earth is. And that the better we understand Earth, the better we understand other planets, and sometimes vice versa. So no, I wasn't looking for ancient water, but I was, peering up at the moon from my backyard in Chicago.
Yeah. I had to write an op-ed last year, Michael, and I called it "Looking Down to Reach the Stars."
That's a lovely title. So let's bring in our other guest here, who is Dr. Yue Guo, who is a postdoctoral researcher in physical chemistry in Professor Alan Aspero-Guzik's group at the U of T, where she's developing a new approach for computation using chemical reactions. She is an alumnus from Massey College. She was a junior fellow, and she has a joint honors Bachelor in Science in Physics and Maths from McGill, and a PhD in Physical Chemistry from the University of Toronto, where she studied reaction dynamics of molecules at crystal surfaces with the famous John Polanyi. And she was a great alumni from Massey, and we're so happy to have you. So you're a chemist, so what Professor Sherwood Lollar is talking about is not foreign to you at all, but you're not interested, you're not studying old water. What are you exactly studying, and does her research impact yours?
Yeah, so thank you for the introduction, and I must say Barbara is such a wonderful mentor and friend, and funny enough, it might be the first time we actually talk about chemistry together. So we actually come from different ends of the spectrum of chemistry research. My research is in very clean, controlled environments. I used to work at the single atom, single molecule level, where I can control reactions at the atomic level and look at how it progresses. And this is in a kind of a vacuum chamber at low temperature where we have control over everything. So what I find fascinating is Barbara's work involves the real world, very messy kind of chemistry. And I was actually curious how you can extract all of this, chemical information from what to me sounds like such a, big phase space of parameters, variables, contamination, etc.
Yeah, it's a really insightful question. She was referring to the fact that she's been a real stalwart in our whole Science at Massey program ever since its inception 4 years ago. So we spent a lot of time talking about the Science at Massey program, Massey careers, all kinds of things. Coffee, a love of chocolate. But this is probably the first time, we have actually talked about the details of what we do. I think spectrum is a perfect way of putting it, CU. We, as geochemists who look at chemistry in the earth, sometimes refer to it as bucket chemistry because it's got all the mess of throwing everything into a bucket and trying to figure it out. And it does have some real challenges associated with it. The one I'll bring forward is that some of these fluids are 5 to 10 times more saline than seawater. When you pour them, they're actually viscous enough that you can see the difference between it's thicker water than the kind you'd get out of a tap. You can see that additional viscosity. And all of that additional chemistry, the things that are dissolved in it, are not only fascinating because they are what microbial life takes advantage of. That's what the microbial life is living off of, is the chemicals dissolved in that fluid. But it causes a real technical challenge. So we do a wide variety of things. We actually do the field work, but a critical part of the field work is also bringing it back to the lab. So all of the work we do is also underpinned in the laboratory by experiments, by modeling, by all kinds of more traditional chemical approaches that allow us to sort of do the hypothesis testing. So we go from complexity to more simplified controlled systems and then back again. And it's that dance back and forth between the complex messiness of the real world and what we can do in the lab or with more simplified models that allows us to once again sort of stumble our way forward in this journey of exploration.
That's fascinating. And I don't want to get into the details of chemistry modeling, but I do have a lot of questions there. But you mentioned kind of microbial life in there. So I was wondering, what does life look like in this water? So just to give some background, I'm currently modeling some chemical reactions that could be useful for a chemical computer. And one of those is these autocatalytic reactions or these self-propelling reactions that keep going on and hopefully kind of give us hints as to how life would start. And so what does that look like in your experiments, in your research, and what does that tell us about how we can find life on other planets?
Yeah, this is one of the most fascinating questions is, and you're sort of inferring to it, is almost philosophical. And because there are large aspects of this that really work your brain in a different way and force you to look at questions almost from a philosophical point of view, as well as the sort of ethical questions that Michael raised. And so by philosophical point of view, what I'll bring forward is this major question of, if we're looking for life on other planets, we can do two things. We can go and we can look for life that looks like Earth. That can work. That's part of what we do. But if that's the only thing we do, then we're going for the possibility of really making a big mistake. Because if we don't recognize that life elsewhere might look different, then we run into the possibility of really missing something. And this is actually even more than a philosophical question. We've stumbled over this before. Even when I was a child, we were still taught that all life on our planet is dependent upon the sun. In other words, the entire biological life cycle is dependent on photosynthesis. But then in the 1970s, as they began to explore the ocean floor, and in particular, I think most of you will have seen these beautiful underwater pictures of what they call black smokers or underwater chimneys, where volcanics erupt on the floor of the ocean, and you see what looks like either black or gray or white smoke. It's actually minerals precipitating out of subsurface fluids that are coming up and mixing with the ocean fluids. But again, these are fluids that are very saline, they're full of chemistry. When they went down to investigate those, they never expected to find life. And so there's some fascinating actual audio clips from the Alvins, the submarine that was diving on those vents on one of the major dives in the late 1970s, where they come up to the vents to investigate what they thought would be the physics and the chemistry and the oceanography. And suddenly what do they see? They see life forms we'd never seen before. Tube worms, clams the size of dinner plates. There's a great little clip of the people in the sub saying, "Do we have a biologist on this cruise?" And they didn't, because they didn't expect to see life. At that time, our idea was life is something that would be connected to the surface. So in the deep, dark parts of the ocean, except for remnants of food that might be trickling down, we had an idea that life couldn't live down there, that the deep, dark parts of our planet were not habitable. And that's because we hadn't thought about a different form of life. And that is what we call not photosynthetic life, but chemoautotrophic life, or more chemolithotrophic, literally rock chemistry eating life. And so we now know, even from our own planet, that it's very dangerous to assume you know what all of life looks like, because you can begin to find life that is operating under a different set of, not DNA principles. The DNA factories are the same, but the metabolic, their ways of getting energy from our planet were substantially different. And that was a major revolution in our understanding of life on this planet. So we don't want to make that mistake if we go elsewhere.
But in a way, it's a great story about not having blinkers and being open to reimagining constantly what we know, and getting insights from other disciplines. In a way, it's a great interdisciplinary stories about, where's the biologist when I need one? You know,
and it actually has implications to our problems here today, because it's really from looking at these kinds of systems that I have colleagues who are microbiologists who study the limits to life for certain bacteria, for certain viruses. What's the range of temperature and pressure they can sustain? What's the range of chemicals that they can survive? Yeah.
Well, indeed, I was going to bring you all together a little bit on these questions I have to ask. Have you thought, when you're looking at our crisis on COVID-19, are they insights of your research outside of keeping an open mind and looking at all avenues that you can bring to bear? Or are they things that that have made you reflect a little bit on what's happening around us these days?
That's for all three of us, right?
Yes.
Yeah.
Yes.
So why don't we start with Michael and then?
Michael, how did you survive what are your thoughts as an educator on COVID-19? We can't hear you, Michael, so
sorry there. I think I had myself on mute. I wanted to give Dr. Lollar and Principal Des Rosiers the floor. As someone in the education school, as someone working in education, I'm thinking about how teaching and pedagogy and content delivery has been forced to change, or has been forced to move even more to the virtual realm. So I'm thinking a lot about teachers who have had to scramble overnight to develop all virtual curricula. Thinking about universities that are now perhaps even more being asked to deliver virtual classrooms. So I'm thinking about those individual teacher and student experiences, and also maybe what it means for the long term. Might this be used as an excuse for school districts or universities to put even more content online? And there are pros and cons to that.
So are you going to be able to continue your exploration of space? How do you do it now? Do you just do it by yourself and put things online?
That's a great tie-in to my other hat, my astronomy education hat. So actually, while you were talking, I was just making a note to reach out to some of my astronomy education colleagues to see maybe if we could do a virtual planetarium show. I think there could be even greater need for a virtual stream right now, given all these kids that are at home, parents who might be looking for an outlet for their kids to do something interesting and educational. So yeah, we're brainstorming right now what some virtual astronomy education would look like. And me personally, I'm stuck just looking out over the balcony at the moon and Venus, which are up right now.
So what about you, Dr. Guo? What are the implications of COVID-19? Certainly, I think I'm sure on your life are huge, but on your research, any thoughts there?
Certainly, it's wonderful to see the chemistry and biochemistry community come together to solve this problem. There are people modeling COVID-19, the molecules, modeling the proteins involved, and looking at whether AI can be used to enhance drug discovery and so on. But for me personally, I think it's, I kind of feel a lot of humility here because, there's a temptation coming from a math and physics and physical chemistry background to try to model something but really, we don't want armchair epidemiologists. There's a lot of models that exist out there. It's interesting to think about the limits of how we can study a system, what parameters, what we know, what we don't know. In fact, some of the code that I had been writing before can be repurposed for a simple model of what does, compartments of people look like, and when we have exchange between compartments, so kind of simulating quarantines or isolation and whether people can leave those boxes or not. But I'm tempted not to venture too far out of my area of expertise. But I have some colleagues who are doing kind of the harder work of studying the biochemistry and the larger molecules involved, which is not my expertise.
Well, I think we all will be challenged a little bit in thinking with hard questions about COVID-19. I think it has stimulated in all areas of expertise a rethinking of some of the things that we may have taken for granted, or anyway, it has accelerated our thinking on some issues. I'm a legal scholar, so for us, certainly, I think the scope of emergency powers, what are the limits of confinement, and so on. So we need to just confront new realities. So Dr. Sherwood Lollar, I was going to ask you about I'm intrigued by old water, not just because I'm getting up there and getting older, but so it is different than the current water. Does it help us solve some of our environmental concern, or is it just an indicator, or just a little bit of a way of measuring what could go wrong on our environment. What's the link between your research, basically, and environmental protection?
Right. Well, I think the key thing is that that's really the other half of what I do. I actually work on water in all of its glory. Do a lot of work on near surface water, and in particular, developing tools to identify whether or not remediation techniques, cleanup techniques on our contaminated surface water work or don't work or can be made more efficient. So I do a lot of work on near surface water, on drinking water supplies, on remediation, all very applied and practical stuff. But then I also am interested then in water from the top all the way down to the bottom. So I think what's interesting is that these waters show us that our concepts of the hydrological cycle need revival. As we teach them classically, we talk about the fact that all water on the planet is on some time scale, that might be tens of thousands of years or even a million years, circulating. But what we found here is that there are, in fact, pockets of the planet where you have probably a different component, a disconnected component of the hydrological cycle, what I've been referring to as the hidden hydrosphere. And we're only now beginning to think about the implications of it. It has practical implications. For instance, that high salinity creates operational problems for either deep science labs or the mines. And in fact, all of this work began initially as an applied study, understanding the implications of the salinity of those fluids on mining operations. If I take a screwdriver under there and stick it in that water, that thing is totally corroded within 12 hours. So it's very applied. And yet then on a fundamental level, though, it has these implications about the origin and evolution of life. So I think one of the biggest issues around these is understanding the diversity of questions that you can actually ask with any of these phenomena. It really ranges from very applied to very practical, and then also to some very fundamental, almost gee whiz questions related to life on other planets.
Well, that was interesting to hear you say that. So that's the journey began then in a kind of an applied way, and then discovered, as you described, a new door that opened up about thinking about this old water and its lack of substances that are not in the new water. So almost a transformative discovery in your field then.
Yeah, and our colleague Dr. John Polanyi would talk about this so eloquently, because he always points out that this idea that we have applied and fundamental and that somehow these are two different things is really a false argument. The two are deeply intertwined, and it is often that we have either applications coming out of something that seemed very curiosity-driven, or the other way around. These things are deeply intertwined, and we have not been good at picking winners. We don't know where that critical piece of information that we need is going to come from. And so to set up these ideas that we have applied and fundamental research, and to make decisions about funding on the basis of that is not a very smart strategy.
Yeah, so it's kind of interesting to hear you there, because that's another that could be a subject of dialogue in itself, about the spectrum from applied to curiosity driven. I'm opening up to questions from the floor and from our virtual floor, from our audience out there, and see whether there's any questions. And here it comes. Yeah, for sure. So from Peter Martin, thanks, Barbara, for this stimulating conversation. The Earth is about 4.5 billion years old. How old is the old water that you've discovered? Can you say it in simple terms, how you measure the age of this water?
Great. Thanks, Peter. Much appreciated. Nice to have you here. Yes, I can. All of the tools that we use are like all chemical tools. You actually get a range of information. So the question is analogous to being asked, and I'll take us back, say, 10 years, what is the age of the Massey community? Well, we could have had an average age. I don't know what it would have been. Let's say 40, but that would have stretched from the youngest, most precocious junior fellow who's coming into graduate school at 16 to Dr. Ursula Franklin, who at that time would have been about 85. So the question is actually, what is that mean age? What is the youngest and what is the oldest? And those are three related but extremely important questions for us. So Peter, to answer your question, the mean age for these fluids is about 1 billion to 1.5 billion years. That's the average age. What's fascinating is the oldest drop is actually a series of xenon components, and I won't go into it more than that, but we're using the multiple and wonderful and kind of freaky isotopes of xenon to show us that the oldest components of those rocks are of those waters are actually almost as old as the rocks themselves. Specifically, the xenon isotopes in the fluid match the atmosphere at the time. So we know what the very oldest is. We know what the average is because that's taken from a variety of chemical processes that we then mean to see what they all tell us. And they all tell us 1 to 1.5 billion years old. But one of the most important questions that we're still grappling with is what is the youngest drop in the old water? Because arguably, if life is in that water, and we now know that it is, the life could be as young as the youngest drop. It could have come in with that youngest drop. And so trying to understand the youngest drop is an extremely important future question because it's actually not easy. It's one of the more difficult aspects of the question. We know the youngest drop is not modern. As I mentioned earlier, modern water is easy to identify. And it's quite clear that there's no modern water associated with these ancient fluids. They're isolated. But whether that youngest drop is hundreds of millions of years old or 800 million years old, or this is the kind of thing we're still trying to evaluate. And because of its importance for the life question, it's a particularly exciting and intriguing challenge.
So that was going to be one of my questions. So what's the future? Like, what are the new things that you have to discover to continue in your work, but also continue to explore this hypothesis of life? So if this youngest droplet has to be identified, the age of the youngest one, anything else?
Well, a big aspect of this is, again, coming back to the exploration. You'd be astounded how little we still know about life in the subsurface of our planet. As we go down, as we go down to perhaps, 1 kilometer or so, there's a fairly abundant literature that's developed. But as we go below 1 kilometer, in particular into the systems we're looking at, at 2 and 3 and 4 kilometers, there's literally a handful of studies that have been done to understand these systems in detail and to know what lives in them. So it is really as if we have identified a new part of the Earth and we're really only just opening up those doors. So a great deal of it is really trying to understand the generality of these phenomena, to take a look at various places and then compare them. Is what we find in the deep Earth similar to what we find in the deep ocean? And how do each of those compare to what we find on the surface of the planet?
And does it matter where? Like, is it, I was going to ask you about, is the old shield of Canada the same as some other old rocks somewhere else in the world?
That too is one of the burning questions. Because if we do think that in many of these cases what this is about is colonization of the subsurface, then what drives that? How does a microbe get 4 kilometers down? So we're investigating things like places where there have been meteorite impacts in the past to see if that could have opened up the crust enough to provide more pathways and see if in those places we see greater penetration of younger fluids and more life than we might find in the place where we found the billion-year-old water. And that's just one of many hypotheses we're using to fan out all over the world to really try to expand our frontiers of understanding about these systems.
So I have another question from the audience here. Ricardo is asking, I understand that Earth underwent a period of early bombardment. during which oceans may have evaporated and early life been obliterated? Are we the survivors of bacteria that hid in these unground lakes?
That's absolutely something that has become a major topic of conversation. Of course, back to Darwin, we have this idea of the life evolving in a warm little pond. But what that very insightful question is pointing out is that we now understand that the early time period on our planet was a turbulent one. As I mentioned, I mean, you might have looked at Mars and decided that was a better bet for a place for life to arise. Our planet was having a rather hard time of it. We were having major changes in the nature of the degree of water on the surface of the planet, in the early atmosphere, and indeed this period of late heavy bombardment. And so it's definitely a key question that's being asked these days. Is it possible that life arose in many, many, many different places, but if it arose on the surface, it was less likely to survive than something that might have, in fact, arisen in the subsurface? And so we have colleagues, such as my colleague at Princeton, T.C. Onstop, referring to not a warm little pond, but a warm little fracture. And so, indeed, that's an extremely important question around the origin and evolution of life aspect that gets brought into this research.
So the warm little fracture. Oh, here's another question as well. Is a follow-up from Peter Martin. What about the prior history of this ensemble of old water? How does the Earth and possibly Mars even come to have water? Can this be generalized to planets that form around other stars? Again, referring back to our earlier conversation about beyond Mars.
Yeah. Peter's referring to some extremely important questions about what we would call the inventory of water on our planet. Where did it all come from, in addition to how did it form and how did it circulate? And so these questions of the degree to which the water that we have here is formed from the original materials, or that water was actually brought in by these bombardment processes. There are still important questions going on around resolving that inventory understanding of what we have in our shopping basket here on Earth and on another rocky planet like Mars, and how that might be different from the ocean worlds. So these are very large and important scientific questions that are still being grappled with within the planetary science and astronomy communities. Again, where they become important with respect to life is that, in fact, there's been arguments made that maybe life didn't arise on Earth at all. Mm-hmm. Perhaps either the ingredients for life, that which formed the prebiotic materials from which life eventually arose, perhaps that came from the bombardment. We certainly know that there are many meteorites and the kind of things that Peter works on in interstellar dust have many organic carbon compounds associated with them. That would have seeded the Earth. Similarly, is it possible that in fact life came from elsewhere and colonized the Earth? I know it sounds like we're stumbling into science fiction, but in fact this is a very valid scientific question. It's not in my area, but it's an area of research referred to as panspermia.
So I have Dr. Guo with a question.
Just following up on what you're saying, which is fascinating, Barbara. You mentioned earlier on Jules Verne. I was thinking of Frank Herbert's Dune.
Yes.
In terms of the ingredients of life, is water a necessary component?
Well, it's a necessary component of all life as we know it. So then the question becomes, can we envisage life in other liquids? Because I think that there's a number of ways of answering this. Life as we know it requires water. Can we envisage life that might be able to evolve and survive in a liquid that is not water? There are people who study this and have made certain arguments that might be theoretically possible. Similarly, we understand that life as we know it is all carbon-based, but anyone who knows Star Trek knows that in fact there is, and in fact it's not just Star Trek, it's not science fiction. There are arguments that silicon has certain chemical characteristics that make it similar enough to carbon that one could at least theoretically imagine on an alternate planet silicon serving the same fundamental role that carbon does here. So I'm well beyond my own areas of expertise here, but there is a wonderful report done from the National Academy of Sciences in the United States from about 10 or 15 years ago, which we all refer to as the Weird Life Report. And it delves in enormous detail, as these National Academies studies do, into this question exactly of what might life look like elsewhere if we had something other than liquid water, if we had something other than carbon, what could we envisage? So I think best, given that this is well outside my own area of expertise, I think if you Google National Academy's Weird Life Report, I think this thing actually pops right up.
But I have another question. So actually was exactly where I was going, because I thought it was so interesting to have the reference to literature, to philosophy, to what does life mean, and why do we define it in this chemical consumptions? Are we doing the same mistakes that we've done before when he said it could only be there if the sun is there? So Allison is asking, I was intrigued by Barbara's reference to literature and philosophy and their impacts on her journey. Can she speak to her views on multidisciplinary education and what values arts and humanities can have on the scientific fields?
Oh, it's essential. I think it's a false thing we put forward to when we try to argue that there's actually scientists and engineers over here and somehow their brains work differently than people who study other things over there. I think that if you take a look at you can test that. And you see, particularly if you walk around Massey, there's not a single person there that fits into that. You see already, and again, I can refer to people like my amazing colleagues, Dr. Polanyi, Dr. Ursula Franklin. You can see it. These are people whose passions and interests are broad and dynamic, and that openness to not only new ideas, but also ideas coming from other disciplines is precisely what leads to them being so good at the part at which they've decided to focus their expertise. I think we're all like lenses. By reflecting light coming in from different wavelengths and different angles, that's how we have the most power on the thing that we decide to focus on. Certainly for me,
that's a beautiful image.
Let's
bring in the young voices here of Michael. How has literature or arts influenced you in your journey?
Absolutely. And actually, I wanted to pivot for a second and ask a follow-up question to what Allison, our guest on the YouTube channel there had, which is a question about your education journey, Dr. Sherwood Lollar. If there's folks out there who are interested in being the next generation of ancient water explorers, I'd be curious, perhaps others would be curious to hear about what your education journey was like, how you ended up where you were, and what advice you might have for future ancient water sleuths.
Well, I think I'll go right back to my dad's advice, because I think it was beautiful. He always just said, take each step, or two things, I guess. One, figure out what looks interesting, stick your toe in, because if it's not, you'll find out by doing, and then redirect. And the other thing he said was always, if you have a series of options in front of you, pick the one that keeps most options open. Try to avoid closing doors by your decision making. And I think that's what allowed me, the only insight I'll put in my education is I always tried to do that. I always tried to take the course that would allow me to keep the most doors open. So you might have some words on that too.
Oh, certainly. I think, there's people who kind of advise me to take a very classical path, and I kind of always tried new things and took on new challenges. My background's in math and physics, but I had the opportunity to work with Professor Polanyi, who's in chemistry, which required picking up a lot of chemistry knowledge, and I thought, I can't pass up this opportunity, and to learn from such a wonderful scholar and brilliant mind. So I think you want to be let yourself be guided, and take whatever opportunities available to you, and you never know where you end up. And right now I'm doing theoretical chemistry and computer science, which I didn't think I would, but it's fascinating, and I'm learning so much and helping me kind of tie in all these different concepts and see the world in terms of different systems and the relation between concepts. It's wonderful. And that's where also I agree with the arts and humanities and literature. I mean, there's so many connections in the world, and kind of you find inspiration in the strangest places.
So let me, there's just one more comment, and then I'll have to close it for today and invite you to tune in for so I just want to say thank you very much for being on Massey Dialogues today. It was wonderful to hear. What a fabulous subject to think about old water, the importance of what it could reveal for life elsewhere in the universe. So I want to thank you very much, all of you, Dr. Sherwood Lollar, Dr. Guo, and Michael OShea for being part of Massey Dialogue for today, April Fool's Day.
Not a joke, I hope.
And I want to invite you to come back tomorrow at 5 o'clock. Tomorrow we're exploring with Yue Guo whether basic income could be thought about as a solution when we experience pandemics like COVID-19. So a great topic for discussion.
Yeah.
Next Tuesday, I'll have the opportunity to have a conversation with Lorna Goodison. She is the Jamaican Poet Laureate. She has just received the Queen's Gold Medal for Poetry. So it'll be wonderful to have her here on Massey Dialogues. On Wednesday, we'll talk a little bit about new research on minority rights. And on Thursday, I'm inviting the Junior Fellows' perspective on COVID-19. What does it mean for their future, how do they see it? And what can we learn from that perspective? So thank you all for being here, and hope to see you again.